Hello, dear students. This is Dr. K. Anandarachakan, Associate Professor of Chemistry, Islamia College, Vaniyambadi. From this class onwards, we shall discuss about the applications of infrared spectroscopy in organic chemistry. First, let us see how the infrared spectroscopy is better than UV visible spectroscopy. See, the infrared spectroscopy has good number of absorptions. It shows a rich array of absorption bands when compared to UV visible spectroscopy. So because of this, one single infrared spectrum gives a wealth of information, gives a lot of information. So both UV visible and IR spectroscopy, both of them are absorption spectroscopy. But infrared spectroscopy gives you a lot of information when compared to UV visible spectroscopy. See, what is an IR spectrum? The IR spectrum is a record of the percentage of absorbance versus frequency. And in IR spectroscopy, the frequency or wavelength of absorption is expressed in wave number. What is wave number? 1 by lambda, that is your frequency. So that is actually called as the wave number. See, the infrared spectrum is having a wave number from 4000 to 667 centimeter inverse. So if the frequency is in this range, that is the frequency of the electromagnetic radiation is in this range, say 4000 to 667 centimeter inverse, it is called as infrared spectrum or infrared region. In terms of wavelength, it is 2.5 to 15 microns. Suppose if the wave number or frequency of absorption is from 12,000 to 4,000 centimeter inverse, the region is called as near infrared region. And the region from 667 to 450 centimeter inverse, 667 to 50 centimeter inverse is called as far infrared region. The frequency expressed by wave number nu bar is simply given by the formula E is equal to Hc, E divided by Hc. Because we know that energy E is given by Hc lambda, Hc nu. So nu is inversely related to lambda. So E is equal to Hc by lambda. 1 by lambda is your wave number. Nu bar is equal to E by Hc. So this is the simple formula for calculating the frequency of absorption, which is expressed in wave number in IR spectroscopy. Now, let us see the reasons for the absorption of electromagnetic radiation. See, we know that in UV visible spectroscopy, the reason for the absorption of electromagnetic radiation is electronic transitions. Promotion of electrons from the LUMO to the HOMO. It requires energy. So the molecule absorbs energy and electrons are promoted. In IR spectroscopy, electromagnetic radiation is absorbed For what purpose the energy is absorbed, or through what way the energy is absorbed? It is through the molecular vibrations. So in an organic molecule, we have different atoms. The atoms are connected by the chemical bonds. The atoms connected by the chemical bonds are in a constant state of vibration. Each and every chemical bond has its own vibration, and it has its own vibrational frequency. So let us understand the molecular vibrations through this simple video. I have a video presentation. From this video, let us try to understand the molecular vibrations. Through this video presentation, let us try to understand the molecular vibrations by comparing it with a ball, metal ball attached to a spring. Let us imagine that we have a fixed support. You have a steel ball. The steel ball is attached to this fixed support with the help of a spring. Now what I do is, if I pull the ball in this direction, then what happens? The steel ball will go out and it will come in. Steel ball will go out and it will come in. So this is your stretching vibration. The same steel ball, if it is attached to a fixed support with the help of a wire, if I push it down, it will go down and it will go up. So this is your bending vibrations. So the stretching and bending vibrations can be understood from this simple example. Let us consider a hydrogen molecule. We have a hydrogen atom connected with another hydrogen atom. There is only one sigma bond between the two hydrogen atoms. So the chemical bonds are just like our spring-like structures. If these are your hydrogen atoms, and imagine that they are connected by a spring. This is the center point. This is the center point, or this is your just like your fixed support. So if you stretch the steel ball in this direction, it will undergo stretching. The same thing can be done in this direction also. So in both the directions, the steel ball attached by a common spring can stretch. If the stretching is uniform, then it is called as symmetrical stretching. So the steel balls both are going out and coming in, going out and coming in. Symmetrical stretching. The same steel balls, suppose if they are connected by a spring and this is the center point, suppose if the steel balls stretching in this way, when one is going in, another one is going out. When the other one is going in, the other one is going out. See? One is going in, another one is going out. Coming in, going out. Coming in, going out. So this is your asymmetric stretching or anti-symmetric stretching vibration. So, it is very clear that a simple molecule like hydrogen can show two types of vibration, stretching and stretching is of two types, symmetrical stretching and asymmetric stretching. Let us consider another molecule, namely water, H2O, where a hydrogen is connected with oxygen. So this is your, see, these are all the spring-like structures. In such a situation, it can bend. Both can bend inside, both can bend outside. Okay, so the molecules through their bonds, they can show bending vibrations. So the bending vibration is of different types, and I will discuss all those things in the example given in the discussion, in the following discussion. Let us come back to the slides to understand the bending vibrations. So in bending vibrations, we have different types of bending vibrations. See, the bending vibration is of two types. One is in plane bending and another one is out of plane bending vibration. See, when the molecule is undergoing bending vibration, then part of the molecule may come out of the plane. See, the two OH groups, they may come out of the plane. If the part of the molecule, because of the bending, if it comes out of the plane, it is called as out of plane bending vibration. Because of the bending vibration, if the molecule remains in the same plane and bending takes place, then it is called as in plane bending vibration. See, imagine a water molecule. The OH groups are in the plane of the cell phone screen or in a sheet of paper where you are drawing the structure. If the OH groups are not coming out of the plane of paper or plane of the cell phone screen, then it is called as in-plane bending. The in-plane bending is of two types. That is, both the groups are getting in. That is, it is just like the action of a scissors. If you move the scissors handle, then what happens? The other ends, both the ends are coming in. They are going out. So this action is called as scissoring. And such a bending vibration is called as scissoring in plane bending vibration. Both the OH groups can bend in the same direction. And they will come back. They will go, they will come back due to bending. And such a vibration is called as a rocking vibration. And in this rocking vibration, the molecule will not come out of the plane. So we have two types of in-plane bending vibration. One is scissoring and another one is rocking. Coming to the out of plane bending vibration, the OH groups are coming out of the sheet of paper or plane of the cell phone screen. Both the OH groups are coming above the plane and going below the plane. It is called as out of plane bending vibration. Such a vibration is called as wagging. See, one of the OH group may go below the plane and another OH group may go above the plane. So in such a case, we have another type of vibration called as twisting. Just like our twist dance. So the out of plane bending vibration is of two types. One is wagging, and another one is twisting. So we have molecular vibrations. The molecular vibrations are different types. One is your stretching vibration and another one is your bending vibration. There is another name for this bending vibration. It is called as a deformation. Stretching vibration is of two types. One is symmetric and another one is anti-symmetric or asymmetric stretching vibration. And coming to the bending vibration, we have in-plane bending vibration and out-of-plane bending vibration. Once again, the in-plane bending vibration is of two types, scissoring and rocking. And out-of-plane bending vibration is of two types, namely wagging and twisting. Now, let us see how the molecule is absorbing electromagnetic radiation because of these molecular vibrations. See, the molecular vibrations, when they are going for a stretching or bending vibration, then the polarity of the molecule is changed. There is a change in the dipole moment of the molecule. So, let us discuss the number of possible vibrational modes in a molecule. If we have a non-linear molecule, organic molecule containing n atoms, for example, methane. Methane is a non-linear molecule. Carbon dioxide is a linear molecule. Hydrogen is a linear molecule. Water is a non-linear molecule. So if we have methane containing n atoms, here n is equal to 4. 4 hydrogens and 1 carbon, so 5. For such a non-linear molecules, the number of possible vibrational modes are 3n minus 6. So number of atoms in methane is 5. 3 into 5, 15 minus 6, 9 possible vibrational modes are there for a molecule of methane. Suppose if the molecule is a linear one like carbon dioxide, then the formula is 3n minus 5 modes. This is the formula for calculating the number of possible vibrational modes in a molecule containing n atoms. So a linear molecule has 3n minus 5 modes of vibration. For example, in carbon dioxide, we have 3 atoms. So 3 into 3, 9. 9 minus 5 is equal to 4. Carbon dioxide will show 4 vibrational modes only. See, I told you that when the vibrations are taking place in a chemical bond, there is a change in the dipole moment due to the stretching and bending vibrations in the organic molecule. And this becomes a basic condition. Only those vibrational modes which produce a change in dipole moment are absorbing electromagnetic radiation in IR spectroscopy. And those vibrational modes which are not showing a change in dipole moment, they will not absorb electromagnetic radiation. And they will not show an absorption in IR spectroscopy or in the IR region. Just like IR spectroscopy, we have another absorption spectroscopy that is called as a Raman spectroscopy. Of course, it has very few applications in organic chemistry. That's why we don't study Raman spectroscopy in IR spectroscopy in organic chemistry. In Raman spectroscopy, the rules are just opposite. It is also based on the molecular absorptions, and those vibrational modes which are producing a change in dipole moment will not absorb electromagnetic radiation in Raman spectroscopy. Only those vibrational modes which are not producing a change in dipole moment will absorb electromagnetic radiation in Raman spectroscopy. So if you make a comparison between infrared spectroscopy and Raman spectroscopy, then the rules are just opposite. The vibrational modes which are IR active are Raman inactive. So once again, let me explain. Because of the stretching and bending vibrations, the chemical bonds in a molecule are in a constant state of vibration, and those vibrations are called as the vibrational modes through which the electromagnetic radiation is absorbed by the molecule. If a molecule has n atoms and if it is non-linear, then the number of possible vibrational modes are 3n minus 6. If the molecule is linear and if it has n atoms, then the number of possible vibrational modes are 3n minus 5. All the vibrational modes are not absorbing electromagnetic radiation. Only those vibrational modes which produce a change in dipole moment are absorbing electromagnetic radiation in IR spectroscopy. And if there is no change in dipole moment, such a vibrational mode is inactive in IR spectroscopy. See, already we have seen that the energy E is related with the terms, namely E is equal to hc nu. If you modify, replace nu by lambda, then E is equal to hc by lambda. And I told you that 1 by lambda is expressed as wave number or nu bar, frequency 1 bar, wave number. See, a formula has been derived to calculate the frequency of absorption of a chemical bond through which two atoms are connected in a molecule. So the formula for calculating the frequency of absorption nu bar is given by 1 by 2 pi c square root of k pi mu. This formula is given in William Kemp, and based on this, some problems are worked out. Please go through William Kemp, Organic Spectroscopy by William Kemp. There you will find a few solved problems. This will help you in understanding the frequency of absorption and its calculation. Based on these problems can be asked in competitive examinations. So nu bar is equal to 1 by 2 pi c square root of k pi mu. K is called as the force constant, and mu is called as the reduced mass of the system. The reduced mass of the system, that is the chemical bond which is connecting the atoms X and Y, is given by the formula mu is equal to mx my divided by mx plus my. So this is about the formula for calculating the frequency of absorption. Nu bar is equal to 1 by 2 pi c square root of k pi mu. So based on this formula, if you calculate the wavelength of absorption of a CH group, the calculation is done in William Kemp. Please refer page number 53. Organic Spectroscopy by William Kemp. The CH stretching frequency is found to be around 3100 centimeter inverse. It is calculated based on this formula. Nu bar is equal to 1 by 2 pi c square root of k pi b mu, where k is your force constant and mu is your reduced mass of the system. Force constant, it speaks about the strength of the chemical bond. We will see later on what is meant by the force constant. The frequency of absorption for a carbon-carbon single bond is 1185 centimeter inverse. For a carbon-carbon double bond, which is calculated according to the formula, it is 1676 centimeter inverse. So theoretically you can calculate. It is compared with the experimental values, and the experimental values are found to be more or less equal to the theoretical values. How about the intensity of absorption in IR spectroscopy? See, already we told you those vibrational modes which are producing a change in dipole moment will absorb electromagnetic radiation. So, the intensity of absorption will be very strong for such vibrational modes. And the intensity is proportional to the square of the change in dipole moment of the molecule. To what extent the dipole moment changes due to the stretching or bending vibrations. So the molar extinction coefficient or intensity of absorption in IR spectroscopy is proportional to the square of the change in dipole moment of the bond in the molecule. So this is about the calculation of frequency and absorption in infrared spectroscopy. See, now let us see the factors that are influencing the frequency of absorption in IR spectroscopy. The formula for calculating the frequency of absorption in IR spectroscopy is nu bar is equal to 1 by 2 pi c square root of k pi mu. K is your force constant and mu is your reduced mass of the system. K, force constant, I already told you, it is speaking about the strength of the chemical bond. Some of the chemical bonds may be very strong, some of them may be very weak. So, a carbon-carbon single bond is less in strength when compared to a carbon-carbon double bond. A carbon-carbon triple bond is stronger than a double bond and a single bond. So the frequency of absorption depends on the strength of the chemical bond, that is expressed by the quantity, namely force constant. Further, the strength of the chemical bond is influenced by various factors. Electronic effects are operating. Mesomeric or resonance effects are operating. The change in the hybridization, that also affects the strength of the chemical bond. The bond angular changes. Sometimes if it is a molecule of cyclic system, then the strain present in the cyclic system considerably weakens or strengthens the chemical bonds. So, the change in the bond angle, the change in hybridization, electronic effects, resonance effects, all these effects can affect the strength of a chemical bond. So, the force constant is an important factor that is determining the frequency of absorption in IR spectroscopy. The next term is pi and c are constant. The next term in the expression nu bar is equal to 1 by 2 pi c square root of k pi mu is mu. Mu is your reduced mass of the system. And already we have seen that the reduced mass of the system is given by the formula mx my divided by mx plus my. So as the mass varies, the reduced mass of the system will vary. It will affect the frequency of absorption. So in the next class we shall see the factors that are influencing the frequency of absorption in IR spectroscopy. Let us continue in the next class. Thank you.